Okay. Any questions about anything? Just a little reminder, and I know we have sort of a skeleton crew today. I guess it's that time of the semester. But we're going to have a test on Tuesday, the 25th, which is 2 weeks from 2 days ago. And before that test, I want everyone to be able to have the homework solutions to homework 3. And homework 3's official due date was today, as you know, and people have been breaking their arms. And, you know, Alex is not the only one with a broken arm or wrist. Shane, who's not here, I saw him, he had a cast on his arm. Snowboarding, skiing, whatever. People are dealing with other stuff, job interviews in New York City, you know. So anyway, but I want to make sure that homework 3 is in next week, like by Thursday perhaps, you know, Tuesday or Thursday, because I want to be able to circulate the solutions before the test. Okay, so that's a warning, and those of you watching at home, goes for you as well. Okay. Any questions about that kind of stuff? Yeah, Drew.
Is there any possibility of moving the midterm to Thursday? It's not the same day as the
If you have 2 or 3 tests in a 24-hour period, and some people have already consulted me about this, like where's Han Min? He's not. You had 3 in 24, right? Yeah. So, yeah. So you got to send me an email, because I'm okay with you taking it like a day late or something like that, but I don't want to move the whole class, because that seemed like an okay date for most people. And it's not good practice to give a prelim like the last class before spring break, in my humble opinion. Okay. Say please. Okay. Where are you flying to? Nice. Is that where you're from, or are you just going to a warm place? Both, okay. Yeah. Yes, Robert. What? Yeah. Oh, right here. Yep. And I'm sure we'll see lots of new faces. Got an email from somebody who said he's taking it exclusively on video note because he has another class that conflicts with it. Let's hope that class doesn't have a test that day too. Okay. What's that? I don't know. I've assumed that a lot of people who did not take this class are not taking it because they're taking 3140, you know, so anyway. Okay, those of you who just walked in, you missed some important announcement. No. Just kidding. All right. So, remember last time we talked about this Metropolis algorithm and the Metropolis Hastings, generalization of it. And there was one thing I omitted to tell you in class. I just want to wrap up that little detail. I posted a handout on this stuff, as you might have read. If you've read your email, you know that. But I omitted one little detail in class that doesn't affect any of the derivations we did. But I want to make sure I cover that just right now before we start simulated annealing. So I left out this one detail when I was figuring out the P's for these, both algorithms, the Metropolis and the Metropolis Hastings. What I did was I neglected to tell you what P of II is. Okay, in other words, these are essentially the diagonal elements of the P matrix for these Markov chains. And the formulas we gave only really held for I is not equal to j. Now you could figure out what PII is by subtracting off all the other PIJs for j not equal to I from 1, because that's what PI has to be. But I think it's worth telling you exactly what the formulas are. So in Metropolis, we had the Q process, the thing that modeled the uniform perturbation, okay, has Q of ij associated with it. And it went like this: P of ij is equal to Q of ij when j is a state of lower energy than I, and equals Q of ij times e to the minus e of j minus e of I over kt when e of j is less than or is bigger than e of I. So this models the fact that when you perturb to a lower energy state, you accept that as your next thing, and this models the fact that you accept it with some probability when you move to a higher energy state. These formulas really only hold when j is not equal to I. What is P of II going to be? This was missing. P of II is going to be Q of II, the probability that you perturb from I and get I back, plus the probability that you perturb to a higher energy state and don't accept it. So this is going to be the sum over all j with e of j bigger than e of I of Q of ij, or 1 minus this. So it's going to be 1 minus Q of ij e to the minus e of j minus e of I over kt. This is the probability that you accept j. 1 minus it is the probability you don't accept j. And if you sum over all the j's that you may or may not accept and add that to Q of ii, that's what you get as P of ii. So this was missing last time. And for Metropolis Hastings, it's essentially the same thing, except we don't have this particular form for the distribution. The Q process, again, has Q of ij, and that's a user choice. And you have P of ij is equal to Q of ij when pi sub j is bigger than or equal to pi sub I, and it's equal to Q of ij times pi sub j over pi sub I when pi j is less than pi I. These only hold when j is not equal to I. And the P of ii formula that was missing last time is going to be the same kind of thing here, except instead of having this exponential thing, you're just kind of a ratio of pi's. So it's going to be Q of ii plus the sum over all the j's with pi j less than pi I of the probability you reject j. So it's going to be 1 minus Q of ij pi j over pi I. Okay, and that was missing last time. But it doesn't affect the subsequent calculations, which showed that the detailed balance conditions are satisfied, and therefore in Metropolis, the Boltzmann distribution is the unique stationary distribution of this irreducible Markov chain. And in the Metropolis Hastings, the pi that you're trying to emulate is the unique stationary distribution of that Markov chain. And there's a problem here. I have to change this. This is actually Q of ij times 1 minus e, rather than that. So let me fix that. And the same is here. It's the product. Each term here is the product that of the probability that you perturb to j from I, and the probability that you reject j. Those are two things that happen independently and in sequence. So what I wrote up there before was a little bit wrong. Now I fixed it. Sorry about that. Okay? All right, so that's just a little detail that I missed telling you last time. I hope you understand where these formulas come from. And read the handout. I think the handout is pretty clear on this. But anyway, the whole circle of ideas generated by Metropolis Hastings, a real tour de force. It's a really excellent thing. A big landmark in the history of computational science. And using these things pervades all kinds of applications, physics, economics, whatever. Markov chain Monte Carlo is everywhere. And actually, once in a while when I tell people, I taught my class Metropolis Hastings algorithm, they say, really? We don't have that until our 6,000 level courses. And I'm thinking, well, this is actually not that hard to understand. I think you guys are equipped to understand this, even if you haven't taken a probability course. You know who I'm talking about. Yes, Mohammed.
So what do you mean by when you say we perturb the distribution? What does that exactly mean?
Well, back in the Metropolis algorithm, what you're doing, again, is you're building this family script P of points. You initialize at some point in the discretized state phase space, which we call capital S. Then you perturb by some uniform perturbation to another point in some neighborhood. And the size of that neighborhood and the way you perturb, those are user choices. And then you ask the following question. Is this thing I perturb to lower energy? If so, then I accept that as my next point. If not, I don't reject it out of hand like Matt wanted to do. I accept it with a probability that is smaller if it's much higher energy and larger if it's not much higher energy. So the perturbing part of that algorithm is modeled by this Q of ij process. And in Metropolis Hastings, same thing, except this one you're not even thinking about the state space as being a discretized phase space of a statistical mechanical system. It's just some arbitrary large finite set.
So when you say we're perturbing, is it just that we are considering a certain set of states rather than finding
Yeah, like if in S, Q is the perturbation process. Q is a probabilistic model of the perturbation process. Think of just some big grid, right? You're sitting at a point on a grid. And then you flip a coin and decide which neighbor of that point to look at. That's the perturbing process. Flipping that coin is doing this when you're sitting at I. Okay? You may end up at one of several different J's. Whatever J you end up with after that coin flip, you check and see. Is J a lower energy state than I? If so, boom, I accept it and I move there. And then I start this over again. If not, if J is a higher energy state, maybe I accept it and maybe I don't. If I do accept it with this probability here, and I don't accept it with 1 minus this probability here. If I do accept it, I move there and I do the thing again. If not, I put another copy of I into my set and I redo this starting at I again.
So I mean, is Q like a stochastic matrix?
Yes, yes. Q is always going to be like the transition probability matrix of an irreducible Markov chain in both of these. Yes, Rahul.
In that case, when you flip the coin and if the energy of J is higher than I, and you say, well, I'll reject it with this probability and put the same one. Isn't that same thing as PII?
Well, I could perturb, my perturbation could take me right to PII.
To itself.
Yes.
Okay, and then when you also.
And these terms account for the rejections. If I perturb to J and reject it, this is the rejection probability of J. And this is the probability I perturbed to J. Okay? Yes?
I still don't have a clear understanding of what Q is like. P is the transition probability from state I to state J, right? But Q is the perturbing process.
Yep.
Like perturbing, why do we have these two separate entities? Like either ways we have state I and state J, right?
Right.
And we can model that with P that is the one-step transition.
Yes.
Intuitively, where does Q fit in?
Okay. Did you understand my description of the algorithm before we started using P's and Q's?
Kind of hazy. And a lot of details.
You've got this big grid. Once again, you've got this big grid. And what you want to do is you want to assemble a set script P of points that are distributed according to the Boltzmann distribution. So you pick randomly a point to start with. Okay, I'm going to start here. Okay. Throw that in the set. Now what I do is I look at the neighbors in some random way. So I flip a coin, and that tells me what neighbor to look at. That's the Q process. Just the coin flip to look at neighbors. It's going to be symmetric. Q of ij equals Q of ji, modulo some edge effects, whatever. And it's going to be irreducible as a Markov chain in and of itself, but that's not the Markov chain of the algorithm, because the algorithm, having flipped the coin to look at a neighbor, has to decide whether to take that neighbor and move states or not. Okay, so to form the P for the whole algorithm, which itself is a Markov chain, we have this sort of base Markov chain that is the perturbing process. We model that by matrix Q. And then we have this reject accept thing, and that icing on the Q cake makes for P. Okay? All right. It's a really cool thing, but it takes some thought. Okay, Robert.
So in this one, we're following essentially like a single state. If you had the case where you had like a ball on top of the hill, and you can go either left or right, if you're following a single one and it's supposed to go one way, it seems like you wouldn't really model the probability of going both ways.
Well, you flip a coin to decide which way to go. That's the cue.
But at the end of it, like you would only have one side almost regardless of.
I'm not sure I understand your question. Okay. Mohammed?
Is this kind of like, a Markov chain on another Markov chain and like
No. It's a Markov chain whose state space is this big grid. Okay? You're moving around this grid, and the number of times you hit each state as you move around, the fraction of the time, is going to be distributed according to the Boltzmann distribution by virtue of the way you've chosen the transition probabilities.
But Q is the original transition matrix for that Markov chain.
No, Q is the algorithm constitutes a big Markov chain. The way to understand the algorithm is to think of it as proceeding in two steps each time you choose a new state. Step 1, propose. Step 2, accept, reject. Q models the propose part. But the whole algorithm consists of more. It consists of not only proposing, but accepting and rejecting. If you just propose, you'll just move around in some random way through the phase space without regard to what the energies of the points are. And what you'll do then is just sample according to the uniform distribution. So Q is only part of the story. That's
I guess, if we're drawing like Markov chain diagram, there's a state I and a state J. So it would be something like from I to J, it's going to be Q of ij. From I to I, it's going to be Q.
well, no, from I to J, it's going to be Q of ij if J is a state of less than or equal to I's energy. But it's going to be this lower quantity if J is a state of higher energy. The point is I want to allow myself to search, even if I move from a state of low energy, which is going to be high P state, to a state of higher energy. I want to accept states of higher energy with some small probability. Otherwise, I won't be able to penetrate the state space.
Again, this is for the like we have many molecules, gas molecules throughout that particular chamber, right? And that I to J, is it the motion of one particular molecule or the entire state space?
No. The gas molecules have nothing to do with the dots in S. The dots in S are discretized versions of some 10 to the 36th dimensional space consisting of positions and velocities for all the particles. Okay. Every point in S is a description of a state of the whole box of gas. It's a specification for every molecule of a position and a velocity, or at least a discretization of that. These are good questions. Yeah, it's fair enough. I mean, that's what we're here for, right? That's why it's better to come to class than walk the other way across the bridge. No, we passed each other. I was on the way to class. He was on the way not going to class. Yes, sir?
I had to sit on my porch. It was very hot.
Right. And then the weather. Yeah, okay. Anything else about this before we move on to simulated annealing? Yeah?
So the energy is just, the energy function or whatever for every state is like predefining or...
Yeah, it's like the sum of, 1/2 mv squared plus, whatever gravitational pulls and... Yeah, it's the kind of thing a physicist would know how to calculate. Given an x, he or she could plug it into a formula and get a number. That's the energy of the state. Yep.
So when you're moving from like I to j, I is a certain state of that box, and j is another
Yes.
state of that box.
Mhm.
So it's basically assuming that you're going in time, or let's assume that your motion is in time. So you could go to a higher state, like from time 1 to time 2, right?
Well, the point, think of the box as being in one state
Right.
in real life.
Yeah.
But what you're looking at is you're looking at a theoretical box whose state could be any number of different states, and you're trying to figure out, you're trying to draw a bunch of like a set of states distributed according to the probability distribution on states that Boltzmann postulated. Okay? So don't think of it as like a box that we're running experiments on. Okay? Think of it as a mathematical model for a box that could be in any state.
And probably that starts from one state, and once the probability could reach this second state, right? It's determined according to that formula.
Yes. Essentially, that's the algorithm. The algorithm for picking points from this abstract mathematical model of a physical system. Blah, 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 blah. Okay? You don't have to get it right now, but, I mean, I just want to make sure you understand that this is very important. This is a really important thing that somebody came up with, and it's useful. And now you have a 3-page handout on it. So, okay. All right. Well, anyway, so moving right along, the next thing I want to talk about is I want to talk about simulated annealing, which is sort of one step beyond the Metropolis algorithm. It's using the Metropolis algorithm in an interesting way on an interesting kind of problem. So the next thing I want to talk about is simulated annealing. How many people have heard this at least referred to in some class or other? Just out of curiosity. Like what class have you heard it referred to in, Matt?
Artificial intelligence.
Max?
Design automation.
Yes. Yeah. What? Power systems. Cool. Yeah. Well, actually, this is the origin of simulated annealing was from some folks at IBM in the 70s and 80s. You know what I mean? I'm not saying I'm saying the 1970s and 1980s. There were some people who were doing microprocessor chip layout design. Okay. And so essentially what they were trying to do is they were trying to come up with a way of doing this efficiently. Now, back then, when someone said large-scale integrated circuit, they meant something a lot different from what we mean now. But still, even in those days, the number of possible ways to lay out a microprocessor chip is huge, right? So there's an impossibly huge number of ways to lay out a given chip. And some of those ways are better than others. And as you know, if you've taken any kind of course in chip design or computer architecture or whatever, there's a lot of trade-offs. For example, this is including but not limited to, what you want to do is you want to minimize signal propagation delays. Because, say, you have to have one transistor communicate a 1 or a 0 to another transistor. You don't want that to take too long. You don't want to have things waiting and all that. But you also want to minimize congestion, whatever that might mean. Roughly speaking, the number of wires in the chip. And obviously, if you want to minimize signal propagation delays, you can put a wire between every interesting place on the chip and every other interesting place on the chip. That wouldn't be a good thing to do because congestion, energy consumption, all that kind of stuff. But in any event, you have all these design trade-offs. And essentially what they wanted to do, and this is CAD essentially, was use computers somehow to figure out what to do. So what is their approach? What was their approach? And the three authors of the original paper on this, and I have this one too, I can show you this. This came out in 1983, which is 30 years after this one, the Metropolis one, came out. And it's called Optimization by Simulated Annealing. It came out in Science, and everyone knows that if you get a paper in Science or Nature, you get tenure. Okay. But these guys weren't even academics. They were CAD people. Okay. They were CAD people, and the approach they took, the three names were Kirkpatrick, Gillette, and Vecchi, came up with the simulated annealing idea. Okay, what is the idea? Well, what they did was they looked back at Metropolis. Metropolis algorithm, remember, is figuring out a big set of points, P. So in Metropolis, you assemble a set, script P, of points that are quote-unquote distributed according to P beta, the Boltzmann distribution. Now, at the roughest level, you have this kind of a statement. When P beta is high, so P beta, remember, of x is equal to some constant times e to the minus e of x over kt is high, you have lots of x's in P. This is rough, what I'm saying here. Whereas when this thing is low, you have few x's in P. So you're getting lots of points of high P beta versus points of few P beta in your set script P as you run this algorithm. But look, this being high is the same thing as E being low, right? And this being low is the same as E being high. So let's state that alternatively. So alternatively, the P you assemble contains lots of points of relatively low E and relatively fewer points of relatively high E. So in some sense, what you're doing when you do Metropolis, one of the byproducts or side effects or whatever you want to say of Metropolis is you're finding a lot of points of low energy. Okay. And so in that sense, what you're doing is you're kind of homing in on a solution to minimizing the energy. Okay, so thus, Metropolis is quote-unquote good at finding points of low E, just in a very colloquial sense. So what was their idea? What was their idea? Their idea was, okay, I'm designing this chip. We're designing this chip. Team effort here. We're designing this chip. We have all these trade-offs. Suppose we can embody these trade-offs in some kind of function, E, say, that we want to minimize. Okay, so here is their idea. Let capital S be some model for set of all candidate, and of course this will be not exhaustive, but there will be a set of candidate configurations for a chip. Okay. And like I said, it won't be exhaustive. They'll limit themselves because of physical constraints or fabrication constraints or whatever they have available to them. to some large finite set of configurations. Suppose we can summarize by some function e from S to the reals, summarize the bad effects of whatever the configuration is. So it's something you want to minimize. So this summarizes an objective function on S. And what you want to do is you want to choose a configuration to make this as small as possible. So you want to choose a configuration in S to minimize E. And what they, you can think of some simple things you could throw into an E that you might, for example, the sum of all the lengths of the wires, or the length squared, or something like that, might be some kind of criterion that takes into account the signal propagation delays. The number of wires, simple quantity that takes into account congestion. Sum those up, sum their squares up, take e to them, whatever. You make a function e, script e, that you want to minimize. You want to choose a configuration to minimize e. Okay. So what did they do? How did they use Metropolis to do this? Okay, so what they did was the following. And first I'll describe what they did, and then I'll tell you why they call it simulated annealing and why you might think it might work. Okay, so here's the simulated annealing approach to minimizing E over S. There's a couple of user choices here. First, what you do is choose a sequence T1, T2, T3, and so on and so forth of temperatures. So these are positive temperatures. And I'll put the word temperature in quotes, because we're not talking about temperatures of chips or anything like that. We're talking about the role they played in Metropolis was temperatures that converges monotonically to 0. This is what's called, this Tn, n bigger than 0, is called an annealing schedule. And I have to retie my shoe here, or else I'm going to fall flat on my face in front of you guys, which would be embarrassing. Okay, so that's called an annealing schedule. First, you choose that sequence. Then what you do is you run Metropolis on S at temperature Tn for a while. So for each n, you run Metropolis for a while at temperature Tn. And in order to run Metropolis, you also have to have some way of perturbing, some way of doing the proposal process. So at the beginning, you settle once and for all on a suitable proposal process Q on S. So you might take this huge set of candidate configurations and define what you mean by neighbors, and you settle on some proposal process for doing the first step of Metropolis. Okay? And after you've run the Metropolis algorithm for a while at temperature Tn, I'm missing a Tn here, once that sort of settles out, right? So when this Tn run, quote unquote, quote unquote settles down, if it looks as if you're not sort of altering by each additional step the distribution of configurations you've chosen, you take the highest or the lowest energy, the lowest E configuration in the set you've assembled. So you take the lowest E configuration in the set, I'll call it Pn, script Pn of points you've generated from running the Metropolis at temperature Tn. So during the Tn run, you've assembled a set script Pn. You pick the lowest E configuration you've got there and use this to seed, initialize the Tn plus 1 run of the Metropolis. So essentially what you're doing is you're running Metropolis again and again and again at an ever decreasing sequence of temperatures. And as each run at a fixed temperature settles down, whatever that means, you have to make that choice. That's a user choice. You stop. You find the best configuration in the set of points you've assembled over that run. You use that to initialize the run at the next lower temperature. And you keep doing that math.
Can you explain a little more what you mean by the best configuration, the lowest E configuration? Like a subset of P event, or?
Okay, E is this function that summarizes badness of configuration. The higher E is, the worse the configuration is, the lower E is. So your goal is to find a low E configuration.
Okay.
Okay? That's going to be a chip that has low propagation delays and also low congestion, say. So your goal is to find a low E configuration.
But so say like you're doing your Tn run, like your Pn is getting bigger and bigger and bigger, and it settles down. Like what do you do with that P of n, like to see? Like
To see whether it settles down?
No, not to see whether it settles
Oh,
down.
you go into that Pn and you evaluate the E's of all the points, which you've actually already done by running the Metropolis. You have to evaluate the E of everything you hit. So you keep a running record of the E values of all the configurations you discovered on the Tn
And
run.
then, and then you choose some of them?
No, you pick one. You pick the lowest, or if there's a tie, you randomly pick one of the ones that has
An
the...
entry.
Sorry?
So it's like a single element of
Yes,
Oh, okay.
exactly. You pick the lowest E configuration, singular. That's going to be 1 point in S, and you use that as the initialization for the Tn plus 1 run.
Okay, gotcha.
Okay? And you keep doing this. You keep doing this. You keep doing this. Mohammed.
So when for the first time we're running this, we just choose a random.
Pick a random config, yeah. Or pick the one we used last design cycle. Or actually, you know, when I talk to students about the project teams, sometimes it sounds like when they have to redo everything the next year, sometimes they have to reverse engineer what they did last year because people kept really bad records, right? So it's almost like picking a random configuration to start your new design. Is that the case for project teams, folks? No? Will? Violet? Documentation. Whose fault is that?
Everyone. Every single person on the team.
Every single person on the team. My friend Nate Parsons, though, he seemed to be a good record keeper. Maybe not. Heavily commented code everywhere, you know. Right. Okay. Well. Yes, Alex.
So, you, like, why would you sleep not all
I'll get to that. I'll get to that. Good question. That's why, you know, that's why it's called simulated annealing. Okay. Rahul.
So you choose random T.
No, you don't choose a random T.
Right.
You pick a sequence of T's converging monotonically to 0.
Okay.
Those are just numbers.
Just numbers.
Any numbers you want.
Right. But when you choose that T right? So I'm looking at this graphically, right? So assuming you have a Tn, and you find the points within like neighboring.
No, no, no. Tn is a parameter of the Metropolis algorithm.
Okay.
It's not anything to do with the search space.
Right.
It has to do with how you search the space. That's all. Okay. All right. Well, I want to get to Alex's question. He says, why this whole sequence of TNs, blah blah blah, and how does that go? This raises an issue. I'll tell you in what sense this converges to a good configuration in a moment. But let's wait a minute. Okay, let's ask the following question. If we're just looking for high E, or sorry, low E is what we want, note that the P beta, okay, is going to be spiky around low E things. Or I guess spiky doesn't have an E, we decided, right? Is that correct? Yes, okay. Is spiky around, spiky high, to be explicit, I'll draw a picture in a second, around low E configurations. And it's more so when T is low as opposed to when T is high. So this, for example, suppose these ticks I'm writing here, these are all low E configurations. So these are all low E configurations. And the axis here is like the search space S. If you're looking around a relatively high temperature, this is what P beta is going to look like. But if you're looking around a relatively low temperature, it's going to look something like this. Just really spiky around these low E configurations, right? So this is for a lower T. Thus, the low E configurations stand out more pronouncedly at low temperature, okay? At least with regard to the P beta. If you just look at the functional form of it, it turns out, the e to the minus e over kt. If t is low, that's a very high absolute value exponent, but it's negative kind of thing. Okay. So the bottom line is that low t implies that the low E configurations, quote unquote, really stand out in your P beta graph. So why not just pick a low temperature and run Metropolis at that low T? Instead of doing this elaborate Tn thing. So why not just pick a low T and run Metropolis at that T? Anybody have a reason for not doing this? Kyle?
You get stuck at like some local minimum, but there could be another one that's further out that because you are starting with like low probability of accepting something that's higher, you just won't get the.
Yes, that is in essence is what's going on. There's always a problem about getting stuck at low minimum. Okay? It's bigger when P is spikier. There's more inertia tying you to a local minimum when P has a really high spike around that local minimum than when P has a not so high spike. So the problem is that for a low T, which means really spiky, P implies that it's easier to get stuck at a local minimum of E. it's harder to move away. Your acceptance probability of a higher energy, you have to, in order to move away from a local minimum, you have to accept a lower or a worse configuration to move away from that. You have to accept something of higher E. And when you look at the probability of acceptance in the Metropolis algorithm, that's going to be really low when T is low. Okay, and E is a higher E, or you have a higher E configuration. Okay, so an extremely low T means you have a really spiky. So why do we have a sequence of T's going down and reseed and all that kind of thing? Well, when we run it at these higher temperatures, we're less likely to get stuck at local minima, and we do a lot of exploration. So thus, when doing Tn runs for the higher T's, and higher T's in the annealing schedule are just lower N's, what we're doing is exploring the configuration space more completely. So we explore S more widely. And hopefully, since we're using the best E configuration we get in every run to start the next run, as we go through this process, and by the way, this is a heuristic optimization process. There's no theorems yet or anything like that. As we go through this process, once we get to a global min, maybe that's when we want to stay there. Okay? So that's why we want to be running it at a lower temperature. Okay, so we explore S more widely at the early T values, and then you zero in on good configurations when N is big, or T is small. So here we go again with those words I've been telling you about. Exploration versus exploitation. That's a very popular dichotomy in optimization. This is what you do for low T's primarily, or for high early T's primarily. And this is what you do later in the algorithm. You tweak. Once you're near a really good configuration, you just tweak it a little bit and see if there's something better nearby. High T's, low T's, the confusion about the N being low when T is high, all that kind of thing. So let's just say N small, N large. Okay. All right, so that's kind of an answer to what Alex asked earlier. Why do they call it simulated annealing? Have you ever heard of annealing as a physical process? No. Yes, maybe. See, I'd heard of it, but I never knew what it was. I knew it had to do with metals and, you know, right? Yeah. But I didn't know what is annealing, you know. Who's a Mat Sci? Who's taken mechanical properties of materials? 2610. Nobody.
We hear it a lot, but a lot of lingo doesn't sound good.
Okay. All right, so what is annealing? So why did we call it, why called simulated annealing? Suppose you have a metal or any solid, okay, any material that can be either solid, liquid, or gas, as any material can be, and its lowest energy configurations are nice, orderly crystals. Okay, suppose you have a material whose lowest energy solid configuration is an orderly crystal of some kind, you know, with all kinds of whatever, hexagonal symmetry, who knows, buckyballs, all that kind of stuff, right? Diamonds. So it's an orderly crystal. All right. Now suppose someone comes up to you in a whole plaza, right? And they say, hey, you know, I have this blob of material here, and I know that it's...
You run away at that point.
Plastic explosive. You know, I know that you know, I've seen people with really orderly crystals of this that are shiny and beautiful, but this is ugly. You know, this. How do I get this to be in a crystal form? Sounds like a drug deal. Actually, a server in a restaurant I was at in the city said, "Did anyone ever tell you look like the guy on Breaking Bad?"
Yeah. Is Walker White the one coming out for
I don't think I look like him. I mean, and I think of him as more Malcolm in the Middle than Breaking Bad because I never watched Breaking Bad. But anyway, whatever. Okay, so the bottom line is this: someone comes to you in a whole plaza and has this ugly specimen of something that you know, that he knows or she knows, can be found in a crystalline form. Can you help me turn this into a crystal? And you say, sure. What I'm going to do is I'm going to melt it down. So suppose you have sort of an amorphous blob of this stuff. And you want a crystal of it. What you do is you melt it down. Okay? First, and so you have this vat of liquid stuff. And then what do? Do you sort of like flash freeze it to 10 to the minus 59th Kelvin? No. What'll happen then? Jeff?
You'll get a lot of deformations in your crystal.
Well, you have this liquid of it, and you flash freeze it. You're just going to get another amorphous blob. It might look different from the amorphous blob you started with. It will be the shape of whatever vat you've got the liquid in. You know, right? So you melt it down. You don't, quote unquote, flash freeze it. You'll just get another blob. What you do is instead, you slowly cool it down, very slowly. Does that sound like Garrison Keillor to you? No? You don't know? All right, you don't know who that is. Instead, you cool it down very slowly. And hopefully what will happen, you know, is that it'll sort of settle into the crystalline state. And it will if you do it right. So it settles into the crystalline state. If you're lucky or good. Okay, now think of this in terms of energy. What happens when you melt it down? You raise its temperature a lot. So the distribution of possible configurations is going to be Boltzmann, and it's going to have a not very spiky P, right? And the low energy configurations aren't going to stand out. If you flash freeze it, you'll essentially get stuck in whatever configuration you started with. Choose that at random with respect to a non-spiky Boltzmann. It's likely to be maybe not even a local minimum. But if you instead cool it down slowly, essentially what you're doing is you're changing the P beta slowly. So these peaks are narrowing, right? And the configuration can move around, and maybe it'll find a higher peak and all that kind of thing. And hopefully you'll end up with a really good one. Okay, so that's what this is called annealing. This is annealing. Okay? Flash freezing is pure exploitation. This allows some exploration along with the exploitation. I don't want to push the analogy too far, but that's, in essence, that covers what you were asking about. Yes?
So
Michael.
even with the higher P, isn't it still possible that it gets stuck in a
Yep.
local minimum there?
Yep. That's why you have to be lucky and good.
So you just have to, okay.
Yeah.
So the whole purpose of this is that it's intractable to find like a rule minimum.
Right.
How can you even represent, like, how is the discretization of the process? Like,
Well, it's actually, to me, the discretization in this problem, the chip layout problem, is a lot more kind of rationally based than the discretization of phase space in Metropolis. Because you could say, okay, this will be the logical structure. I'll have this gate next to this gate, next to this resistor, next to whatever. You know, I don't even know what's in chips nowadays. Same kind of stuff? Yeah. But yeah, I think the discretization makes more sense, you know, in the... Okay, well anyway, this is annealing. That's why they call it simulated annealing. What can you prove? What can you prove about simulated annealing? Let's take the 3-minute break, and I'll quickly summarize what's known mathematically about this. Yes?
So, in this, like, choosing going from one T to another, right? When you get these sets of T's that you can choose, will it all be a bit, like, there will be a difference. It will be lower than the T that you have. So you choose, like, you can pick T1. You want that T to...
You're done picking, you pick the T's once and for all to start with, and then every time you run a Metropolis algorithm, you run it at that fixed T, and you're picking points in the set S. You're not doing any T picking. T is fixed every time you're picking points in S. T is fixed.
So what are those points in T called?
In S,
In S.
configurations for the chip.
Right. So these configurations, where you're going from one, so you're testing it at each temperature to see which one has the best.
You're running Metropolis at each temperature. You assemble a set of candidate configurations. Okay. Among those, some are going to be low E, some are going to be high E, right? There's probably going to be a lot of low E ones because of the way Metropolis works. So you pick the lowest E1 once your thing is settled down, and you insert it as the seed for the next run at the next lower T. You do the same thing. You find a lot of different configurations. Yeah.
So that T that you get, the lowest T that you get, right?
Lowest. Don't say lowest T.
Sorry, lowest.
The lowest E configuration at the end of the nth run. Yeah.
At the end of the answer, so you get the lowest E. You insert it at the next. Requires no further. That's what starts.
That's the initialization for the Metropolis run at the next T. Yeah.
Just doing that until you. So you do that.
Yeah, I'll get to more into the asymptotics of it as we go on. Yeah. Okay, so let's see if we can finish this up today. Had a lot of good questions. I'm sort of understanding now why I'm a little behind this semester. It's because we've had so many good questions. Okay. What's that? Is that independent of the class, what you're doing? What? Okay. Just kidding. All right, so this is annealing. That's why they call it simulated annealing. What can you prove about this? What is known mathematically? This whole description is kind of like wishful thinking. Hey, maybe I'll find a good configuration for my chip if I do this, you know. What can you actually say rigorously about it? So what are the mathematics behind this? It turns out you can show, under various assumptions, and I won't even get into those, mainly because I don't really know what they are completely, the following. Okay? First of all, I'm going to let S star be the set of all E minimizing configurations in S. So these are the global minima of your configuration badness function. You want to find a configuration in S star. That's the goal. Okay? Sorry?
Isn't S star likely to contain just one thing?
No. Well, there might be many configs that have the same global minimum. Like if you use this brand set 47K resistor versus that brand 47K, you know, whatever. Okay, and for each n, I want to let pi n star be the stationary distribution, the unique stationary distribution for the Markov chain on the Tn run that the Metropolis algorithm leads to. So for the Metropolis Markov chain at temperature Tn. And let pi n star of S star be the probability that that pi n star assigns to S star. In other words, it's just the sum of pi n star of j for all j in S star. That's what it is. It's the weight that that probability distribution assigns to the subset S star of S. You can show, given those definitions, that limit as n goes to infinity, and this is, of course, under these appropriate assumptions, of pi n star of S star equals 1. In other words, over the long haul, the stationary distribution of the nth Metropolis run, the Tn Metropolis run, is going to assign higher and higher and higher probability to the optimizing set of configurations. And that's a good thing. Okay. So i.e., later runs assign ever higher probability to S star, and it's asymptotically equal to 1. Your PNs are going to contain ever more copies of configurations in S star. So ever more configs in S star as n increases, etc. So in this sense, you can prove that simulated annealing works. Okay? By the way, those of you who've seen simulated annealing either in AI or CAD or whatever, how much depth did you go into the math on it? None? Zero? Epsilon? Maybe? Less than epsilon. Okay. Well, anyway, this is something you can prove. Now, this is a very weak kind of convergence result. So this is actually a fairly weak. Kind of convergence. And I'll try to explain why in a sec. It's like a quote-unquote limit of limits rule. Okay, so what do I mean by that? What do I mean by that? Here's the idea. If you let x n k, and here the notation gets a little messed up, x sub n comma k be the state at time k of the Tn run of Metropolis. So on the nth run, you can think of it moving around in the configuration space S as the state of a Markov chain. And if I let x and k be that state, then by our Markov chain theory, the limit as k goes to infinity of the probability that x n comma k is in S star equals pi n star of S star. Because what's going to happen in that Tn Markov chain is this x n k, the state at time k, is going to run around and run around and run around, and as k goes to infinity, it's going to visit S star a fraction of the time proportional to, equal to, the stationary distribution weight of that optimizing set. And thus, saying the limit of that equals 1 is the same as saying limit as n goes to infinity of the limit as k goes to infinity of probability that x n comma k is in S star equals 1. That's what I mean by saying that this is like a limit of limits kind of result, and it's fairly weak. But it's still good news. It's still good news that something that was just something that occurred to people, hey, you know, Metropolis, good at finding low E things. Maybe we can use it to optimize. Let's tweak it, see what we can do. Oh, we can't just do it at a low temperature. We have to anneal. You know, it was a good idea. So if they talked about simulated annealing in another course and they didn't do any of the math, what did they say about it?
Use it.
Use it?
Yeah.
Read about it online, kind of thing?
Yeah. Makes a little more sense now.
Well, I mean, the whole point, we're trying to put Markov chains to work, and this is, Metropolis puts them to work in one way, and this puts Metropolis to work. So by the transitive law of putting to work, it also puts Markov chains to work, right? That's pretty nerdy, I know, but anyway, no one ever said I wasn't right. Okay, all right. So can you make a stronger assertion under stronger assumptions? And the answer turns out to be yes. And leave it to the control theorists, who are closet mathematicians like me. I didn't come up with this, but two of my friends, two of my contemporaries, Bruce Hayek at UIUC and John Tsitsiklis at MIT. They're mainly control theorists. They published a rigorous paper on improving this convergence result. So I'll say they sharpen things considerably. How do they do that? Okay, I want to see if I have their paper here. I think, well, I have a Hayek. Here's a Hayek paper called A Tutorial Survey of Theory and Applications of Simulated Annealing. This came out in 1985, so he did this all in a very short amount of time with Tsitsiklis. How did they do that? What they did was they look at the user choices in simulated annealing. What are those user choices? What's the first user choice?
Q. Or
Okay, Q. The Q. That is to say, the proposal process that you settle on once and for all. Okay, that's one. What's the other one? What's that? Well, that's what Q is. Alex. The TNs. Yeah, the annealing schedule. Okay, so they looked at those two user choices and they thought, what if we can, based on the properties of our E function, choose Q in a special way and choose the annealing process and the annealing schedule in a special way to get a sharper kind of convergence? And essentially, that's what they did. What they did was they made certain assumptions about the E function. And those kinds of assumptions have to do with regularity and depth of bowls around local mins, widths of bowls around local mins, things like that. So e.g. regularity, whatever that might mean. that neighboring configurations have reasonably close E values, that kind of thing. So regularity, depth / width of the sort of bowls around local mins, local E-mins, etc., those kind of things. And they made the TN, the annealing schedule, go to 0 very slowly, very, very, very slowly at a rate whose slowness they quantified. And I'm not going to have time to go through the details, but let me just describe it. Next time I'll do this at the beginning of class. But basically what they did was they made some assumptions about the E. Based on those assumptions, they said, okay, we'll design the proposal process so that we're guaranteed to be able to get out of local mins by a Q jump. That's how it affects the Q design. Then they designed the annealing schedule to go to 0 very slowly, and the rate at which it goes to 0 has to do with the depths of these bowls. And there's some equation they have, some inequality they have that says, you know, if D is the maximum possible depth of a bowl around a local minimum, then Tn has to go to 0 this fast. And then they constructed, it turns out, an inhomogeneous Markov chain whose state approaches S with probability 1. And I'll talk about that at the beginning of class next time. It'll only take a minute. Well, more than a minute, but